Okay, folks, so let's talk about an equation of the form ax plus by equals c. All right, that would be an example of a linear equation. Of course, that's just one form of it. This would be the standard form of a linear equation. Other forms exist, obviously. I know one of the most popular forms of the line is slope-intercept form. When it comes to systems, it's sometimes more helpful to have the equations written in standard form. And that way, it helps us to construct our matrices and what have you as we move along this journey together. Now, with what I've written out, it's all purely notation, right? There are no explicit numbers in there. So just to make the distinction between the constants and the variables that are involved in here, we would say that the equation is linear in the variables x and y. Okay, and by saying that, it should be clear that x and y are variables, and we can assume that a, b, and c are constants or real numbers. And the graph of a linear equation, as you might expect, is a line. And I have an example of the graph of a linear equation. Really, it's just an excuse for me to put in a Watt meme, but Watt and linear equation. And here we have a line, and the equation that they actually are modeling here is y equals mx plus b. But there would be a way from going between y equals mx plus b and ax plus by equals c. All right, there's always going to be a way to do that. So yeah, this is the very, well, I'll call it the germ of the beginning for linear algebra. All right, it's all born from the study of lines, in particular when we start putting more than one line in the same coordinate plane. But before we discuss those sorts of scenarios, I do want to inform you as to what makes an equation linear, because as you'll see, there'll be more and more variables inserted into that standard form equation, yet it still will be considered a linear equation. So you're not just confined to the variables x and y. We can have more in there, provided that the variables satisfy a certain criterion. So it says here, no matter how many variables are present in an equation, if none of them have powers different from 1, okay, that's key there, are not multiplied to other variables, and are not contained inside functions such as logs, trig functions like sine and cosine and tangent, exponentials, etc., then we would consider the equation a linear equation. All right, so things that are bad in terms of the equation not being linear would be situations where a variable has a power different from 1, or if we're multiplying 2 or more variables together, or if we see a variable contained inside of a function, okay, like the natural log or log base 2 or something like that, or even the square root. So with that said, I'm going to get generic here and define a linear equation in n variables. All right, and here's how I typically denote this. I use some subscript notation. I'm going to write a sub 1 times x sub 1. And I'll indicate what each of those are in just a second. And to this, I'm going to add another term of this form, a sub 2, x sub 2. To that, I'll add a sub 3, x sub 3. And we're supposed to have n variables in here, so there are going to be n terms. And since we're not really sure what the value of n is, to be as generic as possible, I'm going to add what's called an ellipses, and then another plus sign with a sub n times x sub n. And I'm going to set the sum of these terms equal to b. Now, each one of these a subscripts, I'll make a little note here, each a sub I is a real number, i.e., they're coefficients. Okay? And then each x sub I is a variable. So we could technically say that this is a linear equation in the variables x sub 1 through x sub n. Now b is a constant. In other words, it's also a real number. Okay, but it's not a coefficient because it's not in front of a variable, right? So I would, consider that, or I'll basically be saying numbers that are on the right-hand side like that they're constants. Now, there's kind of a special case of a linear equation in n variables, and that has to do with a particular value of the constant term b. So we're now going to look at what's called a homogeneous linear equation in n variables. Now, the left-hand side of what we just wrote out will remain the same. So I'll still have those terms a sub 1, x sub 1, plus a sub 2, x sub 2, so on and so forth, all the way down until we get to a sub n, x sub n. But a homogeneous linear equation has a particular value of b on the right-hand side, and that particular value is the number 0. Okay, so anytime we're setting, our sum of terms equal to 0 in a linear equation, that makes the equation homogeneous. And those types of equations play a lot of key roles in linear algebra, so it seems kind of random that we're picking on the number 0 here, but there is a lot of utility with an equation such as this. All right, so that's why I want to define it right out of the gate. So we're going to work on our first example here, where we're going to determine whether the equation is linear. And even though it doesn't require it, I would like us to also classify whether that linear equation is homogeneous or non-homogeneous. But if we come across an equation that's not a linear equation, then there's no point in trying to classify it as homogeneous or non-homogeneous. Those classifications are only for linear equations. All right, so let's take a look at example part A. We have 4x minus 2y plus 3z equals 12. What do you guys think? Would that be a linear equation or something else? It's definitely linear, yeah. The key here is to really just look at the exponents of the variables. All right, all of the exponents of these variables that are present in the equation have a degree of 1. All right, we don't have any variables being multiplied, and they're not inside of things either. So no powers are different from 1, and the rest of what I just said. All right, so this is definitely a linear equation. What do you guys think? Is it homogeneous or non-homogeneous?
It's
non-homogeneous.
Non-homogeneous, you got it. Yep, so I'll write it out this way for now. Non-homogeneous. But to shorten that up, we can just write capital N, capital H. I'll be totally fine with that. Example part B, we have 3 times the square root of x sub 1 plus x sub 2 equals 2. Let's assume the variables are x sub 1 and x sub 2. Is this an example of a linear equation?
No.
Nope. And I'll indicate a reason as to why that is. It has to do with the fact that x sub 1 is inside of a square root. So we have this as part of one of the terms, and recall that we could rewrite this as x sub 1 to the power of 1/2. So, whichever way you want to view it from, either, there being the square root or there's a power different than 1. Either way you slice it, this is not a linear equation, and no need to classify it as homogeneous or non-homogeneous. What do you guys think about the equation in part C?
Yes, it is.
Definitely. Yep. So there's definitely a homogeneous. Well, I gave gave my next question's answer away. This is definitely a linear equation. And as you already heard, this is going to be a homogeneous linear equation because the constant term is 0. So I'll say homogeneous. And in the future, we can just indicate that with capital H. How about part D? example part D. So let's assume that the variables are x, y, and z. It's definitely not a linear equation. I'll say no. And the reason for that, as you can probably tell, is due to the fact that we have a variable inside of a function. Okay, the argument of cosine contains our variable z. So the fact that we have cosine z makes this nonlinear. What about example E? We've got 3xy equals 0.
It is a linear.
Well, let's assume that our variables are x and y. So you'll notice that there's a product going on, specifically involving x times y. So we're not allowed to have that in a linear equation. So I'm going to write down no. And the reason for that is x times y. And another way of just kind of explaining, the reasoning why this is not a linear equation has to do with the fact and how we define a general degree of a term. So I'm not sure if they're still teaching this, in the lower classes, but when it comes to a polynomial that has more than one variable involved, the degree of each term is based on the number of variables involved, specifically a sum of their exponents. So if we look at 3xy, the variable x has a power of 1, that's its exponent, and the variable y has an exponent of 1. The degree of a term such as that would be the sum of the two powers, which is 2. So, we have a term that has a degree different than 1, which is another explanation as to why this is not linear. Does that make sense? Question, yep.
So is it possible that x and y could have the same base? Is that what that means?
It is possible if x and y were equal to each other. That would have to be stated beforehand. But in terms of trying to determine whether or not we have variables with a power different than 1, we can kind of approach that from a degree standpoint. So when you have a term with a mixture of variables, that term has a degree, and its degree is determined by the sum of the exponents. So I'm not going to write this as like something to a power of 2, but that doesn't take away from the fact that the degree is 2. So when it comes to a term with multiple variables, the degree is defined as the total number of variables involved. So for instance, if we had like -2 x squared y cubed z, the degree of this would be the sum of all the powers of the variables. So we would have a degree of 2 plus 3 plus 1, giving us a degree of 6.
Okay, I got you.
All right, cool. Anything else? If not, then what do you guys think about the equation in part F?
It's a linear.
Definitely linear. Yep. All right. Non-homogeneous. Okay, let's take a look as to why that is. We could attempt to write this in standard form. One way of doing that is to maybe bring the -5x over to the left-hand side. That'll give us 5x plus y plus 3. And 8 to the 1/3 is the cube root of 8 in disguise. So that would give us 2. And we can just subtract 3 from each side. We have 5x plus y equals -1. And you'll notice that the constant term on the right-hand side is not 0. So this is definitely a non-homogeneous linear equation. So nice job, Drake. And there we have it. So we can start combining non-homogeneous with homogeneous, or keep it all non-homogeneous, or keep it all homogeneous. But either way, once you start mixing two or more of these so-called linear equations together, you form what's called a system of linear equations, or linear system for short. So these will be collections of linear equations, typically two or more, and the number of variables will really depend. So in some cases we might have two equations and two unknowns. In some cases we might have two equations with four unknowns. All right, so we got to open ourselves to situations such as the latter one. But I'll give you some quick and easy examples just to show you that it is something that we've probably worked with in the past. So an example of a linear system here could be something like 5x plus 2y equals 10, and 2x plus 5y equals 8. So something as basic as that. And of course, you can indicate that you're considering both of these at the same time, with half set of braces, just kind of enveloping them, if you will. So this would be an example of a linear system, particularly one that has two equations and two unknowns. And you'll notice that both equations are written in the standard form. But it doesn't have to be confined to anything basic like that, to be quite honest with you. You might have three equations where one is not in standard form. So say something like y equals 3x minus 17. And there might be a second equation where you have simply x is equal to 4. And then you might have another equation where you've got 2x plus z is equal to 0. So there's lots of different ways of mixing in equations with each other. When it comes to solving a system, in our textbook or through Wiley Plus, obviously those equations will be provided to you, but they could be provided to you in a variety of formats. Don't always expect the system to come in standard format. It could come in y equals mx plus b, or a mixture of the two. But when we go to solve them, that just might require an extra step for putting them all in standard form and going from there. So, what is all this alluding to? Why linear algebra? Well, linear algebra really helps us to examine whether or not a system will have a solution, and also helps us to address how many solutions a system will have. Okay, as you're probably aware, some systems might have many solutions, whereas you might have a system with no solution whatsoever. And it's those concepts that really form the foundation of linear algebra. So it says here, one major aspect of linear algebra is examining the number of solutions to a linear system, as well as the techniques and processes for finding them, and also their implications, a lot of the times geometric implications, and there are going to be some theoretical ones as well. So it probably is a good idea to define what a solution is. First of all, a solution of a linear system consists of values for the variables, okay, that are solutions to each equation. Okay, and that's key there. All right. When we find a solution to a system, we have to make sure that it works in all of the equations that were provided to us to begin with. All right, and to solve a linear system means to find the complete solution set to the linear system. All right, and basically what that means is we want to find all the values of the variables that make the equations true. So with that, I want to provide some notation somewhere in this blank spot here. I'm going to call this solution notation. And this will be the case where we have a system with n unknowns. So let's say that we found the value of the first unknown, x sub 1. And generically speaking, I'm going to call its value s sub 1. So I'm writing out some parentheses, and it's basically going to look like an ordered pair, but just more generalized. because we're to assume n variables. So let's assume the first variable solution is s sub 1, so that would start out this ordered pair. The second variable solution is s sub 2, and let's go all the way down to the nth variable solution, which I'll call s sub n. And a solution such as this must satisfy all the equations in the system. So if we're saying that this is a solution, it must satisfy all equations in the system. Now, the notation here actually does have proper term or proper terminology. This is often referred to as an ordered sorry for the screen dragging. It's often considered an ordered n-tuple. Oh, when it's just two variables, we could call that an ordered pair or an ordered two-tuple. If it's got three unknowns, and there's a solution for each of them, it would be an ordered triple or an ordered three-tuple. But of course, we start running out of those words like quadruple, quintuple, heptuple, and so on and so forth. So it's a little easier to refer to a solution of this type of format as an n-tuple. All right. But of course, just S1, S2 ordered pair is just fine. If it's S1, S2, S3 ordered triple, or ordered triple is just fine. So generically speaking, for something like this, we refer to it as an ordered n-tuple. So I mentioned that there are some geometric implications of solutions to linear systems, and we'll start with probably some familiar cases here. This is just some geometry that's involved when you have a linear system with two variables. There are really just three things that can happen in terms of the solutions. So in each one of these diagrams, I have one line that's already plotted, and we're going to plot a second line in each one of these. And case 1, case 2, and case 3, we're going to draw our second line a little differently just to examine the variety of scenarios that arise when you have two lines plotted together in the coordinate plane. So here we have the line, looks like it has a negative slope. One thing that can happen is that there can be a second line that maybe goes like this, in which case it would appear as though the two lines intersect each other. So one way of describing what we're seeing is to say that the lines are intersecting. Now for a line that's intersecting with another line, you probably know that their point of intersection is pretty important, right? Point of intersection appears to be somewhere right here, and that point of intersection actually serves as the solution to the linear system that corresponds to these two lines. But it looks like they're only intersecting in one spot, which is actually the case here. So in terms of number of solutions, there's something to be said about that. How many solutions would there be to something like this?
One solution.
Just one solution, yep. Yep. So a system like this does have some terminology involved with it as well. It's called a consistent dependent system, which I'll add right here. You could also have two lines that appear to not intersect at all, in which case that would be the situation where the lines are parallel. If two lines are parallel and they're not intersecting each other, are there any solutions?
No.
Right. So this would be a situation where the number of solutions is 0. And anytime we have a system where we have parallel lines that aren't intersecting and the number of solutions is 0, we can consider that system as an inconsistent system. What's one more thing that can happen if we have a line plotted with another one?
I don't know, is parabola an option?
Parabola would be for a nonlinear equation.
Infinitely solution.
Yeah, infinitely many solutions or one line on top of the other. You're exactly right. Yep. Another thing that can happen is our second line coincides with our first line, in which case any point that's on the first line is also going to be a point on the second line. And so, you know, technically any point on the first or second line would serve as a solution to the system. So all of the points on these two lines would serve as solutions. And since lines, you know, are indefinite in the sense that they extend in both directions forever and ever, this would indicate that there are infinitely many solutions. So I'll indicate that with the infinity sign, a little hyphen there, and the word many. So infinitely many solutions. And I like to describe a system such as this, or what the lines are doing, as overlapping, or one line is on top of the other. I liked what Ross put in the chat bar there. And there's a special name for a system such as this. It's called, this is actually consistent dependent. I'm noticing I may have forgotten something with the case 1 scenario. This is consistent, my apologies for this, by the way, consistent independent. Sorry about that. So just make sure you add IN to your dependent word of case 1. Case 3 is a situation where it's consistent dependent. And the major deal there is it's dependent in the sense that, you know, the solution coming from one line depends on the solution from another line, since they're overlapping each other. Okay. Any questions so far? All right, so as you add more and more of these variables into a linear equation, there's some modification of geometry that happens. So for example, when we plot an equation with two unknowns, you know, we usually do that in the coordinate plane, which is two-dimensional, right? That's a two-dimensional apparatus. When we have something that, when we have a linear equation with three variables, that would usually be an entity that lives in three-dimensional space. And what it produces when we have an equation in three variables is a plane. And we can add a fourth variable, in which case, you know, we work in 4 dimensions, and we can continue on until we work in what's called n-dimensional space, which is something that we'll be doing quite often in this class. Even though we can't visualize things that are in 4 dimensions or higher, we can still do some algebra in those dimensions, which I think is kind of a cool thing. So anyway, the graph of the equation ax plus by equals c produces a line in 2D. Now I want to give you some notation for two-dimensional space. We would usually write that as capital R with a superscript of 2. And we say this notation as 2 space. Now adding a third term with our third variable on the left-hand side of you know, the standard form equation, as I mentioned, that's going to produce a plane, and that plane is going to live in three-dimensional space, which there's a notation for that as well. It's capital R with a superscript 3, and we would read that as 3 space. In the most generic sense, you know, we could have an equation with n variables, right? So I'm going to write our linear equation in n variables. An equation such as this produces what's called a hyperplane. and I'm going to say that that's produced or lives in the, or I'm not going to write ND, I'm just going to write this as R with a superscript N. And we would refer to that notation as N space. Does anybody know what we would refer to, or what we would read this as? That would be MySpace. Anybody remember that social media platform? MySpace. Yeah, it definitely got beat out by Facebook once that came on the scene. But yep, I'm sure my MySpace account is probably floating around out there still somewhere. Nothing interesting though. So, yep, that's just kind of me joking around. But anybody have any questions about what we just went over for that? All right, I'm getting some feedback in my my headphones here. Anybody got their mic on with some feedback going on in there? Maybe want to check that. All right. So I want to take a look at the case where we have multiple planes plotted in the same three-dimensional coordinate system. And regardless of us increasing the dimension and changing the geometry of what our equations produce, we would still be concerned about the number of solutions to the system that corresponds to these entities. So we're now going to examine visually the number of solutions to linear systems that have three unknowns. All right, and solutions in a scenario such as this are really identified the same way as they were with the two-line situation, where we want to find any points of intersection between the three planes. All right, now if it's going to be a solution, remember, a solution has to satisfy all the equations involved in the system. So if there's a solution to the system, it should correspond to a point that's on all three of the planes at the same time. Okay, if we find that there's a point that's on two planes but not on another plane, then that's not going to be a solution to the system. All right, solutions have to satisfy all the equations, and from a geometry standpoint, the solutions will be points that are on all of the planes at the same time. All right, so we're going to work on the first row here, and we'll try to identify where the solution or solutions are, and then we'll just make a note of how many solutions there would be to that system. So I want to make a note before we do that. Note right here, there are three planes in each diagram. All right, and the reason why I mentioned that is some of these diagrams look like there might be only one plane or two planes, but we're to assume that there are three planes in each diagram. Okay? So starting with the first box of the top row, we've got three planes. We've got this one right here. We've got one kind of coming out of the page. Then we've got this one right here. And do you think there's a point of intersection?
Yes.
Yep, definitely a point of intersection here, and maybe you might be spotting that point as being right here. Confirmation on that?
Mm-hmm.
Yep, that right there would represent a solution to the linear system with three equations and three unknowns. And that's actually the only solution. That's the only point where all three planes coincide with each other. And you can kind of think of this as, like the corner of your room. the floor and the two walls that meet up with each other, there is one point that is in connection with, all three of those planes, the floor and the two walls, and that would be the very corner of your room, right? Which, by the way, it is winter, so if you are cold, I always recommend standing in the corner of the bedroom because it's always 90 degrees there. No? All right, so the number of solutions to this system is just one. Okay, so just that corner point. With our second diagram, we're seeing three planes again. Here's a plane. There's a plane. And we've got this as a plane. Are these planes intersecting each other? If so, in how many spots? Yeah, actually, there's more than just one solution to the system. If you take a peek right here, okay, that line that is formed when you intersect these planes in this way serves as solutions to the system. Now, keep in mind, these planes extend, indefinitely, in their respective directions. And what ends up happening is, we can describe this solution in a geometric way. The solution would actually be a line, all right? And a line has infinitely many points on it, so the number of solutions to a system like this would be infinitely many. Okay, so in one case, we have just one solution, and the geometry of that solution is a point. In another case, we've got infinitely many solutions, and the geometry of that solution is a line. Now, what's happening in the third diagram is all three planes are on top of each other. Okay, so any point that's in one plane is going to be a point in the other two planes, and so on and so forth. And so, this is another situation where we have infinitely many solutions because planes are infinite in the sense that they extend, in their two directions. And so infinitely many solutions for something like this as well. But the geometry is different in this scenario, okay? We had a point, a line, but the geometry of our solutions for the third scenario is actually a plane. All right, so that's going to be something that we address from time to time, is not only the number of solutions, but can we describe the geometry of this linear system just by virtue of the solutions to it and their format. Now, I mentioned that all three all diagrams have three planes in it, and this last one looks like there's just two, right? But what we're to assume with this last diagram is that two of these planes are intersecting each other, so or on top of each other, I should say. So let's maybe assume that this plane right here is on top of a plane in the same position, and then here's our third plane. Can anybody describe the geometry of the solutions to something like this? So all three planes are intersecting each other, and yep, they intersect each other in a line. So all of these are points of intersection, and they would trace out a line, yielding another system that has infinitely many solutions. So let's look at some other scenarios. We'll work on the bottom row now. Here we have three planes, and just by virtue of the way these things are drawn, it appears as though all three planes are parallel to each other. And I'll let you know that that's something that we can assume in this diagram. So all three planes are parallel to each other, but they're also all separated from each other. So do you think there's ever going to be a point that lies on all three planes at the same time?
No.
No.
No. So the number of solutions to something like this is simply 0. Now another diagram where it looks like there are less than three planes, but kind of like the very last box of the top row, let's assume that we have two planes overlapping each other. So let's say that this is one plane that's overlapping with this plane, and then we've got the parallel plane that doesn't intersect those other two. So in terms of solutions to a linear system with three unknowns, okay, a solution doesn't change. The definition of a solution doesn't change its meaning. So if there were a solution here, it would have to be a point that's on all three of these planes at the same time. Now, granted, there are infinitely many points that are on the blue and green plane at the same time, but none of those points would actually also be on the orange plane. So, in terms of a solution, there's not going to be a point that's on all three of the planes at the same time. So this is another no solutions situation. Do you think there are going to be, excuse me, do you think there are going to be any points that are on all three planes at the same time with our next diagram?
No.
No. Now, if we were just considering two planes, okay, then we could see that there are, infinitely many solutions with a situation like that. But, with three planes here, a solution should be a point that's on all three at the same time, and there's not going to be a point that satisfies that. And it wouldn't take too much of a stretch of the imagination to find that there are no solutions to our very last diagram as well. So let's make a connection between the lines cases and also these recently developed plane cases. With regard to what happens in terms of the number of solutions in the two-dimensional situation, we saw a system having one solution, we saw a system having no solution, and we saw a system having infinitely many. Now, if we look at the conclusions for the intersecting planes, or lack thereof, we do see that a system can have one solution. We also see that a system can have infinitely many, and we also see that a system could have no solution. And before I make the jump to the overarching concept here, go ahead with your question, whoever chimed in.
So I had a question with that plane and what was the other one? R2 and R3.
This one
Can
here?
you repeat that one more time, please? Yes.
Yep.
And the other page, which was?
Yep. So let me color code these planes real quick. So a solution to a system such as this would have to be a point that's on all three planes at the same time. Now, if we just consider two planes at the same time, maybe the green and the orange one, then these would represent solutions. But that would be only if we had two equations with the three unknowns. Another scenario might be if you have the blue and the orange plane, only those two planes plotted together, in which case you would have infinitely many solutions to a system like that. But do keep in mind that we're to assume a linear system with three equations and three unknowns. So there's actually no point that is on all three planes at the same time. All right, these pink lines that I had drawn would be kind of like special cases where there's just two equations with the three unknowns. But assuming three equations with the three unknowns, there's not going to be one point that's on all three planes at the same time. So you might have a point that's on two planes at the same time, but whatever two planes that point is in common with, it's not going to be in common with the third plane. So because there's no possibility for a point to be on all three planes at the same time, there's actually going to be no solutions to a system like this. So a solution has to satisfy all three equations at the same time. and you might have a solution satisfying 2 equations, but it wouldn't satisfy the third. Does that help out?
Yes, thank you.
No problem. So this is where we'll end things for today. Very important concept that does come to bail us out every now and then throughout the course. So regardless of the number of equations and unknowns, right, there are only 3 things that can happen with regard to the number of solutions, okay? A system may have 1 solution. A system may have no solution. Or a system may have infinitely many solutions. Of course, I was writing that as infinity sign dash many. But what's pretty striking about this is that there are no other possibilities. So let's look at what it's not saying, okay? This is not saying that a solution can have 2 solutions and only those 2 solutions. That's not possible, okay? If you find that a system has 2 solutions, I got news for you. There's actually infinitely many solutions to that system, okay? This is not saying that a system can have only 100 solutions, okay? Because if you have 100 solutions to a system, there are infinitely many to it, all right? So when it comes to systems, no matter how chaotic and humongous they might look, you can always bank on there being 1, 0, or infinitely many solutions to that system, and there are no other possibilities. That makes sense? When we solve a system that has 1 solution, you're going to have concrete numbers for your variables. When we solve a system, there will be indication as to there being no solution, at some point, during the algebra of it all, and there'll be ways of determining that with matrices when the time comes for it. And then there's also going to be ways of identifying there being infinitely many solutions with matrices, but we're going to investigate that right here, right now, without the use of matrices, but rather just with some old-fashioned skills that we can use to solve a linear system. And then we'll look at a way of creating formulas which would help us to generate specific solutions that are part of the infinitely many solutions. All right, so obviously it's impossible to write out all the solutions to a system that has infinitely many, but should we be curious and want to know some points that do work for the system, there would be a way of generating those. Okay, so with that, I'd like to visit a 2x2 linear system here. We got 2 equations, 2 unknowns, and the instructions are plain and simple: solve the linear system. All right, so there are a couple ways that we can do this. We can use a substitution method. We could use elimination, and there's another way as well. We could use graphing. I would like to stick, though, to the algebra way of solving these things. So let's take a look at one way of doing this. So we have 2 equations. Let me indicate the first one as equation 1, the second one as equation 2. I'm going to do substitution, and what that's going to require is isolating one of the variables in one of the equations. And if you look at equation 1, I think the easiest variable to isolate is the variable y. So I'm going to pick on equation 1, where it's 3x plus y equals -4. I'm just going to bounce this 3x over to the right-hand side to get y equals -3x minus 4. And now we're assuming that the variables x and y are the same 2 variables in both equations. So if we have this expression for y, -3x minus 4, what it means for us is that we're allowed to replace 3x minus 4 into the y that's part of the second equation. Now when you do that, you're going to get 6x plus 2 times -3x minus 4 equals -8. And we'll go ahead and distribute the 2 to clear parentheses. It's going to give us 6x minus 8 equals -8. Now the 6's cancel out, and we're ultimately left over with -8 equals -8. And there's no more solving that we could do for x. But what we're left with is a true statement regardless of what x is and regardless of what y is. So you could pick any pair, x and y, provided it satisfies the equations above, and it would be a solution. The fact that we get -8 equals -8, that's an absolute truth here in mathematics, and this would actually imply that there are infinitely many solutions. Doesn't really matter what x and y are. -8 is -8. It's not going to change the fact. Okay, no problem. So this system does have infinitely many solutions. Okay, that's the indication via the algebra. Now, if it were no solution, we would see something like -8 equals 5, or -8 equals 0, or 0 equals 1. So a no solution case would be, if we had something like, 0 equals 1, something like that would imply no solution. All right. Now, if we were to do this graphically, what we should expect is there to be 2 lines that are overlapping each other. So what happens if a system has infinitely many solutions, but we want to see just what are a couple of those solutions? What's one solution to it? What's a second solution? What's a third solution? If we're curious about that, then we're going to need something called parametric equations. All right. Now, parametric equations give us a way of expressing the solution to a system in a more concrete way. It allows us to write what's called a general solution to the linear system, and in a roundabout way, we are able to use that general solution to figure out some specific examples of solutions to the system. Now, one way of explaining what parametric equations are as well is that they're equations that allow the original variables of the linear system to be expressed solely in terms of what's called a parameter. So in essence, what we do is we take all the variables that are part of the original linear system and we create an equation for it using sort of like a third-party variable. And this third-party variable is what we refer to as a parameter. So for instance, if our system involves the variables x and y, then x will be written in terms of a parameter and y would be written in terms of a parameter as well. Typically they're the same parameter that you use, although you get different formulas most of the time. And this parameter is like a third-party variable that is allowed to take on any real number value that you wish. And when we pick on any particular value for the parameter, we get specific values for x and y. And so essentially a parameter helps to determine in a roundabout way what the value of x and y would be as soon as you choose a value for it. So to define parametric equations, there is a little bit of a science behind it. So I'd like to go through that right now. So let's say that we have that equation 3x plus y equals -4. Now, reading this from left to right, the variable that comes first is the variable x. And as such, the variable x can be considered what's called a leading variable. Okay, it leads off the equation in terms of the order in which the variables are presented. Whereas the variable y would be considered what's called a free variable. Now, the free variables are what we use to define parameters. Okay, so free variables help you to create these third-party variables. And what ends up happening is that once you've created these parameters using your free variables, you're able to write the leading variable in terms of them. Okay, so for something like 3x plus y equals -4, since y is a free variable, we would define that as a parameter. And the most common letter to use for a parameter is t. So knowing that y is a free variable, one step of defining a parametric equation would be to say let y equal t, where t is a parameter. Now, one thing to note is that t can take on any real number. So t, I'm going to write this notation, looks like a rounded out capital E. Does anybody know what that symbol represents?
All real numbers?
This symbol here is our math notation for is in. Oops. Also known as an element of. And to the right of this is where I'm going to write interval notation for all real numbers. Okay, so essentially what this means is that t can be any real number. And so since t can be any real number, and we write the variables in terms of the parameter t, as we'll see on the next page with the difference system, that would generate infinitely many solutions. Okay, so the infinitely many solutions in this context comes from the fact that t can be infinitely many numbers. So how do you create parametric equations in general? That's what I'd like to address next. Number one, what you want to do is solve the linear system to determine whether parametric equations are even necessary. All right, parametric equations are necessary when you know a system has infinitely many solutions. They're not needed whatsoever if you know that your system has no solution, or if you know that the system has one solution. All right, so that's one thing that you want to be aware of. Then what you want to do is determine your leading variables and your free variables. All right, and here's how I indicate it. Let's go back up to this equation, 3x plus y equals -4. Since the x came first, I define that as my leading variable, which means that the y is going to be my free variable. So I'll usually point out which variable is leading and which variable is free. Number 3 says all free variables will be replaced by a parameter. All right, so if you find that you have 2 or more free variables, use different letters for them. That way there's no confusion. So maybe TS, R, W sometimes, or even subscript notation like T sub 1, T sub 2, and so on and so forth. Number 4, you rewrite the equations in terms of the parameters. So what happens is once you define your parameters, there's going to be a way of expressing your leading variables in terms of those parameters that you've defined. So 5 is something I just touched on by saying that. Isolate each leading variable to obtain an equation for it. This will be expressed in terms of the parameters. 6 says this process can leave your paper with equations everywhere. So this is just a matter of advice from Mr. C here, just to be organized with your work with parametric equations. It's very easy to get caught up and lose track of the process of defining them. So I'll show you a 3-step process that I do, which really helps us to avoid making that error. So with that, we're going to use parametric equations to describe the solution set of the linear equation. Now, what you want to be in the mindset of here is that you have a system that you've solved, and essentially you've determined in advance that there are going to be infinitely many solutions. So like with the system that we started out with today, we had 2 equations, 3x plus y equals -4, and then the 6x, and so on and so forth. Really, one equation here is a scalar multiple of the other, in the sense that one of the equations is redundant. You can either pick the first or the second one as being redundant, And we essentially can boil this down to a single equation, and we could boil this down to the equation 3x plus y equals -4. So I just want to point out that you can think of these equations as arising, or us arriving at these equations by use of some substitution or elimination method. Long story short, let's assume there are infinitely many solutions here. So going from left to right, the variable x shows up first, so I would define that as a leading variable. Variable y shows up second, so I would define that as the free variable. Now, the free variables are what you're going to use to define your parameters with. So once we've identified those, we're going to start this three-step conveyor belt process here. I'm going to say let y equal t, okay? And keep in mind t is the parameter. This takes us to a step 2, where we're going to rewrite this equation using t instead of y. So it's going to be x plus 10t equals 2. And this allows us to isolate the variable x, thereby giving us an equation for x which involves the parameter t. The third and final step is just to make a list of your parametric equations. I'll say PEs for short. One parametric equation is created as soon as we've defined a parameter for a variable, y equals t, right? It's kind of like y equals x, that's an equation. Since t is a variable, y equals t is an equation. We also have this one where it's x equals -10t plus 2. So our parametric equations start with x, -10t plus 2, and our variable y equals t. So you'll notice that by using this third-party variable t, x and y are no longer linked together in a single equation. It's kind of like we've busted the equation up in a way that x gets its own equation and y gets its own equation, and both equations are using the parameter t. Now, why is this helpful? Well, one reason why it's helpful is that as soon as you pick a value of t, you almost immediately get values for both x and y. And in fact, if you wanted to, you can construct a table where we can pick some random values of t, and depending on the value of t, we'll get a value of x. We'll also get a value of y. And as an added bonus, we would get an ordered pair that would be a solution to the system. Would anybody like to pick a random value of t for us?
0.
Okay, let's use 0. Yep. So we would plug 0 into the t for the equation for x. That's going to be -10 times 0 plus 2. That means x is 2 when t is 0. And when t is 0, y is automatically 0. So one of our solutions to the system would be 2, 0. Not the only solution, because you could pick another value of t. Value of t? 3, okay. So if you plug 3 into the equation for x, that's -30 plus 2, giving you -28. Y equals t would be y equals 3. And here's another solution to the system, -28, 3. You could do something like -1 if you wanted. Okay, that would make x 12, y -1, and you get another solution to the system. And there are lots and lots of more values that you could pick for t, since t is allowed to be any real number, which means that there are lots and lots of solutions to the system, i.e. infinitely many solutions. Does that make sense?
So this equation has infinitely many solutions?
Yep. This would be a system having infinitely many solutions. Yep, go ahead with your question.
So how would it be if there was no solution or one solution? Would we not get a value for x and for y?
So if it were no solution, at some point, we might see something like 2 equals 3 if we were to solve the system. So that would imply no solution. If it were one solution, then we'd be able to come up, or we would only be able to come up with a value for x, say like x equals 1, and only one value for y, so like y equals 2.
And that's
So
when the parametric equations, we would come up with those.
so if the system has infinitely many solutions, that's when we would need to come up with parametric equations.
Oh, okay.
Yep. So there would be no need to define parametric equations for something like 2 equals 3 or something like x equals 1, y equals 2 when we just get one solution.
Okay.
Yep. All right, cool. So with part B, let's assume that we were solving a system and we found out that this was really the only equation that you needed for your system. That is, like, the other two, however many other equations you have, are redundant. We're assuming infinitely many solutions, and so we're going to write parametric equations for this equation. And going from left to right, x would be our leading variable, y would be our free variable, and so would z. Z would be a free variable as well. So in this instance, how many parameters do you think we're going to have to define?
2.
2, yep. So for this three-step process here, I'm going to say let y equal t. Now, we also need a parameter for z, and we should use a different letter. And I know this is not in alphabetical order, but I'm going to define z as a parameter s. It's another common letter to use for parameters. This takes us to step 2. What we're going to do is rewrite this equation with our parameters instead of the variables y and z. So we'd have 2x plus t plus 4s equals 1. And what we're going to want to do with this equation is solve for x. Okay, so maybe we'll start off by subtracting those two terms over to the right to get 2x equals, and I'm going to write negative t minus 4s plus 1. And then we can divide everything by 2. And we get x is equal to, let's say, negative 1/2 t minus 2s plus 1/2. So x is isolated, and it's also in terms of the two parameters that we defined. So that takes us to step 3, where we'll just kind of catalog these parametric equations. I'll start off with x. Okay, we found that x is negative 1/2 t minus 2s plus 1/2. In step 1, we saw that y is equal to t. And we also saw in step 1 that z is equal to s. And there they are. Now, it's not required, but if you want to see how parametric equations involving two parameters would work to generate solutions, all it would do is just add another column to our table. So you would need a column for t. You would need a column for s. And then, of course, we'll have columns for the three original variables, x, y, and z. And what these generate are actually ordered triples, because we'll have 3 values due to there being 3 variables, x, y, and z. So when you plot infinitely many solutions with, that are ordered triples, one might expect this to form a plane. which is actually what this would be, geometrically speaking. You know, we saw yesterday that if we add that third variable z into a linear equation, that ups the degree or the dimension of the space, and what would be for a system with infinitely many solutions. Okay. Now, what you can do is just pick random values for t and s and plug them into your formulas to get your values for x, y, and z. So for instance, one option for s and t, or t and s, would be 0 and 0, in which case x would be 1/2, y would be 0, and z would be 0, and so 1/2, comma 0, comma 0 would be a solution to the system. You could use 2 and 1 if you wanted, or -1 and +1. They don't have to be the same two numbers. You know, you could use 1 and -1 if you wanted. In which case, if we plug these two numbers into the equation for x, that's going to be -1/2 plus 2 plus 1/2, giving us 2. T is 1, s is -1, and so another ordered triple or solution to the system would be 2, 1, -1. And you can continue picking different combinations of t and s, and depending on what values you choose for t and s, you're going to get a new solution for the system. Yep, go ahead, your question.
On a quiz or a test, would you require us to make a table like this and find those and use any values we want, or could we stop where we create the parametric equation?
Yeah, no, you can stop with the parametric equations. That's
Okay.
usually about as far as I have the students go for that.
Okay.
Yep. But I like to just give a little more detail here, just to show you how we could use them to generate the solutions, just so that you have a better understanding of why we're even doing this, first of all. Because to me, I mean, when I was first learning parametric equations, it just seemed a little random, like, why is this even necessary? But obviously now I have a different perspective on it, and so just want to not leave anybody in the dark here. Yep. So with part C, this is kind of a special case here, where we have two equations, and we have three unknowns here, x, y, and z. Now in our first equation, if we wanted to find leading and free variables, I would understand x being a leading variable and us writing down that y is a free variable and z is a free variable. But with this addition of a second equation here, we might have to modify our understanding of what we assign y as, because in the second equation, y is a leading variable and z is still going to be a free variable. Now, if this is the case, all right, if you find that one of your variables is a leading variable in a different equation, then keep that variable as a leading variable, okay? Don't make it a free variable. So what I mean is, we have y as a leading variable in the second equation, but we marked it as a free variable in the first equation. Leading variable will always trump the free variable, okay? So there's really just going to be one parameter that we need for a system such as this, all right? And that would be the common free variable between both equations, and that would be z. All right, so really just one parameter here. We're going to say let z equal t. Now with that, if we rewrite the first equation using t instead of z, we'll still have the variable y in there, but you'll see that that gets taken care of real soon. If we write the second equation using t instead of z, we get y minus 3t equals 1. Now I want to focus on the second equation. The second equation will allow us to get a parametric equation for y pretty much in one fell swoop. All right, just add 3t over, and we get a parametric equation for y. Okay, so parametric equation for z, parametric equation for y, and what do we do about x? Well, what we can do is, now that we know that y is equal to 3t plus 1, we could plug it back into that spot in the first equation. So we would add x plus 3t plus 1 plus 5t equals 2. Yep, go ahead.
I'm sorry, you might have already said this, but the part where you went from x plus y plus 5t equals 2, and then you went to y minus 3t equals 1, how did you get to that part? Like, which part did you substitute?
So I replaced z with t. So I changed this to t and I changed that to t.
Okay, and then what happened to the x in that equation? Like, did the x
the x is still there. Is that what you're referring to, or?
just the part like in the second equation, the y minus 3t equals 1, like what happened to the x?
Oh, there was an x there to begin with the second
Okay.
equation.
I see. I'm sorry. Okay.
Oh, it's okay. No problem. All right, so let's combine some like terms. X plus 5t plus 1 equals 2. We'll go ahead and isolate x to get x equals negative 5t plus 1. And so at long last, we have a parametric equation for x now. And that's all the variables that we need to write parametric equations for. That's going to take us to step 3. So we'll just kind of catalog these. Oh, I'm sorry. Yeah, I missed that. 8t. That was just an awareness check. No, I'm just kidding. So yeah, the 3t and the 5t do combine to give us 8t. And so we should have x equals negative 8t plus 1. So here we go. X equals negative 8t plus 1. Y is equal to 3t plus 1. And then z is equal to t. And those would be our parametric equations. Okay. All right, so I won't do a table for this one because I would like to go on to our discussion on matrices. But do you guys have any questions before we do that?
So if we go with the table, then we will have t, x, y, and z.
Yep.
Okay.
Yep, t, x, y, and z. Now, I do want to mention that we could have a line as our solution space, if you will, in three-dimensional space. We'll learn later on, this is kind of a spoiler alert, that when we have parametric equations with 2 parameters in them, that traces out a plane, whereas a set of parametric equations with just 1 parameter, that's going to trace out a line. And do keep in mind that that's definitely a plausible object to have as our solution, because as we saw yesterday, solutions in three-dimensional space could be, one of 3 entities. It could be one point, it could be a line, it could be a plane, or there might be some instances where it's the entire three-dimensional space. But for now, we'll just consider our possible solution objects as a point, a single point, a line, or a plane. So that's now going to get us to shift gears a little bit to talk about what a matrix is. A matrix is just an array of numbers, variables, or a combination of them. And later on, we'll actually be putting functions inside of matrices. But what we mean by array is that, it's an apparatus that has rows and columns. And this is one way of defining a matrix in a very generic way, albeit. And in each one of these spots, in other words, in any particular row and column, we have what are called entries. Now, I would like to add some notation to this diagram here. The first row, I like to indicate that with R sub 1, and that would consist of all these numbers or expressions, A sub 1, 1, A sub 1, 2, and so on and so forth. Right underneath that is row 2, and right underneath row 2 is row 3, and this goes all the way down to row M. Now, how do I know that's row M? It has to do with the fact that the first thing that's written in that subscript is M. The first column would be this, those consisting of A sub 1, 1, A sub 2, 1, all the way down to A sub M1. The second column will be to the right of that, the third column to the right of that, and we get all the way down to the nth column. And how do I know it's the nth column? It has to do with what they're writing after the explicit number here, so A sub 1n. All right, so all in all of these items that are populated within this rectangular array are referred to as entries. And generically speaking, we could write an entry as A sub ij. Now, the value of I indicates the row of the entry, and the value of j indicates the column of the entry. So let's get some practice with that. I have a matrix here, and in this example, we want to identify 5 particular entries. The first of those entries is A sub 1, 4. A sub 1, 4 tells us that we should be looking at the number that's in row 1 and column 4. So it might help to mark off the rows and the columns. This would be row 1, this would be row 2, row 3, and row 4. And then this would be column 1, column 2, column 3, and column 4. So it's kind of like a multiplication table where you just cross the row with the column and you multiply, the two numbers that lead off, each row and each column there in a multiplication table. And this one is location, A sub 1, 4. So we want to be in row 1 while at the same time looking in column 4. And the common number that's in both those at the same time is 5. So A sub 1, 4 would be the number 5. Does that make sense? Let's do A sub 2, 2. Okay, so we want to be in R2, so row 2, column 2. Okay, and where they meet up at is at the entry 6. All right, I'll have you folks try this out. Go ahead and see if you can identify A sub 3, 4, A sub 4, 1, and 4, 4. All right, here we go. Or 4, it's going to be 3. Those look good to you guys? All right, so one thing about matrices that's helpful is they give us a way of rewriting linear systems without all the variables. Right, so they allow us to abbreviate linear systems, and there's a special type of matrix that can be created out of a linear system, and that matrix is called an augmented matrix. So let me show you how to create an augmented matrix, and I'll explain why it's called augmented and all that jazz there. Our first system has 2 equations and 2 unknowns. If you think about this from a row and column standpoint, since there are 2 equations, there should be 2 rows in our matrix. Now, there are 2 variables, so you might think that there are going to be 2 columns. Well, in an augmented matrix, for something like this, there are going to be 3 columns because there's going to be a column for the constant terms as well. Okay, so what I'm going to do is write out a bracket for my matrix notation. And by the way, some of the older school instructors use just large sets of parentheses for the matrices. I tend to use the brackets. But in this first row, what I'm going to do is going to write out the coefficients of the variable x and y, okay, without the variables and without that plus sign there. It's going to be 2, and I'll leave a little bit of a space, a little bit of a gap there for the coefficient of y, which is 1. And I'll do the same using the coefficients of the variables x and y in the second equation. So -4 and 6 is what I'd put there. Now we are going to include the -1 in the 42, but to distinguish -1 and 42 as constants versus coefficients, what we do is we put this large vertical bar. It's kind of like a little borderline there, or a little wall, if you will. It really kind of represents the equal sign. But that large vertical bar there is going to separate the coefficients from the constants. And the constants are -1 and 42. And this is what we mean by augmented matrix. And it's called augmented because we're augmenting, or we're joining, in a sense, the constants with the coefficients all in one matrix. Okay, and we use this long vertical bar just to tell ourselves, hey, anything on the left-hand side of this is coefficient, whereas anything on the right-hand side of this is a constant. Now, it's important that all of your variables line up in the original linear system. So they line up here. We have x on top of x, y on top of y, and they also line up in the second system. But if any of your variables are shuffled out of order, you want to make sure that they're all lined up with each other before you throw it into an augmented matrix format. All right, so it's probably not too much of a stretch of the imagination here that this matrix that we're going to write out next is going to have 3 rows, and it's going to be 4 columns with the augmentation of the constant terms. All right, so I'll start with the coefficients. The first equation, 3, 7, and -8. And then 4, -1, and 2. And then 2, -2, and -3. Okay, so those are the coefficients, and I'm going to separate these coefficients from the constant terms, which I'll add in to the right of this vertical bar. So -1, 16, and 5. And that would be the augmented matrix form of this linear system. Okay. Any questions about what we've gone over so far? All right. So we do have a few minutes left. So with that, just a quick note before we transition to section 1.2. What I have down here are some supplemental items that you could work on from our textbook. They're not going to be collected though, although if you want to turn them in for feedback, I'll be more than happy to look through that for you. But you know, some supplemental items, if just in case you know you want a little bit more than what you're getting in Wiley Plus, would be to read through section 1.1 and complete these problems. Okay, they're not required. All right, they won't be collected for credit. It's just some extra practice, just in case you want it.